All right, today we're going to look at a couple of problems involving Taylor series. We'll spend a couple of days on this just because I know it's a topic that you guys need more practice on. All right, so the first problem, they're giving me like a piecewise function for f of x. And it says that f is defined for all derivatives. And then they give me a function g given by 1 plus the integral from 0 to x of f of t dt. All right, so the first question says, write the first three terms in the general term for the Taylor series for cosine about x equals 0. And then use this to write the first three terms for f. So that's really cool. The first part, you're probably going to get some points just for your memorize, right? So just if you know your first three terms in your general term for cosine, because that's memorized because it's Maclaurin, because it's centered about 0. All right, so then I'm going to use that to find the general term for f, or the first three terms and the general term for f. So f says to take cosine, which we have, and then subtract 1 from it and divide it by x squared. So I'm literally taking that series, I'm subtracting 1 from it, dividing by x squared, and then I'm going to simplify that. All right, so when I simplify that, I get the function negative 1/2 plus x squared over 4 factorial minus x to the 4th over 6 factorial, and so forth. All right, so for this one, I'm going to get a point for knowing my memorize. I'm getting a point for the first three terms of f, and then a point for the general term of f. All right, the next question says, use the Taylor series about x equals 0. Find the part A to determine whether f has a relative maximum, minimum, or neither x equals 0. All right, so this was the series that I obtained in part A. And I noticed immediately that I don't have an x term, which means I don't have an f prime term, which means f prime of 0 is 0. I also noticed that my x squared term, which would correspond to that second derivative, is positive, so it's greater than 0. So I know my first derivative is 0, which tells me I have a maximum or a horizontal tangent. But because my second derivative is greater than 0, I know that it's concave up, which means that I have a relative min at x equals 0. So I'm going to get 1 point for determining f prime 0, and then 1 point for the answer with the reasoning. All right, the next part says write the fifth degree Taylor polynomial for g. All right, so g was the function they gave us at the very end of the question prompt. I know I have to work out all of my values, and I need to do this all the way up to like the fifth derivative. All right, so I know that g is 1 plus the integral from 0 to 0. Remember, the integral of 0 to 0 is nothing because it's not moving, so 1 plus nothing is 1. Then g prime, I'm using the fundamental theorem of calculus, so I know g prime of 0 is f of 0, and f of 0, according to my piecewise function, is negative 1/2. All right, so then the second derivative of 0 is the same thing as f prime of 0. And so f prime of 0, based off of my Taylor series that I wrote, I didn't have a x term, so f prime of 0 is 0. All right, so then the third derivative of g is the second derivative of f, and I can calculate that again using my series that I got in the previous example. I know that the second derivative of 0 over 2 factorial was equal to 1 over 4 factorial. Solving that out, I get that the second derivative is 1/12. I'm going to continue this pattern on until I get to that fifth derivative. So like the fourth derivative, I didn't have a fourth x to the fourth term, so I know it was, or the fourth derivative of g is the third derivative of f, and I didn't have a third degree term in my series, so I know it was 0. And then for the fifth derivative of g, it's the same as the fourth derivative of f. And then I set up a little expression to figure out what that fourth derivative was. And I got 1 over 30. From there, once I got all of those values, I'm able to write my Taylor polynomial. Again, that is centered at 0, so it's really just a Maclaurin. I don't have to worry about having like minus or plus anything with the x because it is centered at 0. I just need to include my coefficients, being sure to remember to do like over 2 factorial, over 3 factorial, over 4. Make sure you guys remember to do that when you're writing your series out. So you're going to get 1 point for the 2 of the terms being correct, and then you're going to get another point for the other remaining terms being correct. All right, so next part says the Taylor series of G about x equals 0 evaluated at x equals 1 is an alternating series with individual terms decreased in absolute value. So we know it's all series, we know it's decreasing. So it says use a third degree Taylor polynomial to estimate the value of G of 1 and explain why this estimate differs from the actual by less than 1 over 6 factorial. All right, so the first things first, I'm going to find my third degree Taylor polynomial, again, using the values that I just calculated in the last step. I'm going to go ahead and evaluate that at 1 to get my approximation. And so after I get my approximation, they asked me to go ahead and find the error. Well, because it was an alt series and I used T3, so I used the degree of 3, I know that my next term, which would be a 4, would be my error. All right, so A4, I'm literally plugging in 4 into my general term of that series that I got in the last step, and I get 1 over 30 times 1 over 5 factorial. That number, don't know what it is, it's non-calculated, but it for sure is going to be less than 6 factorial because 6 times 5 factorial is 6 factorial, and then we still have times another 5, so that's going to be less than 1 over 6 factorial. So you're going to get 1 point for the estimate of 37 over 72, and then 1 point for the explanation. All right, next question, it says consider the differential equation, and then they gave it to us. Let y be the particular solution with f of -1 equaling 2. So the first thing I want us to do is use Euler's method, starting with x equals -1 to approximate 0. And we're using 2 equal steps, so I'm going from -1 to -0.5 to 0. Just like when we did Euler's before, we're literally just plugging in, taking our time. So they told me from the question prompt that when f of -1 is 2, so y is 2 when x is -1. Then I need to find dy dx at -1, 2. I'm literally just plugging it into the formula that they gave me, and I get 4. And then I need to multiply that by my delta x. My delta x is a half because we're increasing a half every time. So 4 times a half is 2. And then I'm going to add that to my old y. 2 plus 2 is 4. Doing that process again, plugging in the -0.5 and 4 into my derivative, timesing that number by the delta x, adding that to my old x, I get an approximate value for f of 0 of 17/4. So I'm getting 1 point for Euler's method with 2 steps and 1 point for the answer. All right, so it says at the point -1, 2, the value of the second derivative is -12. So we need to find the second degree Taylor polynomial for f about -1. So they tell me that f of -1 is 2. I can start there. Now I know I need the derivative at -1. So I'm literally going to plug in -1, 2 into my derivative to get 4, which we had earlier from Euler's. And then they told me that the second derivative is -12, so they pretty much gave me everything I needed. From there, I can write out my Taylor series, making sure that I center it around x equals -1. All right, I went ahead and simplified mine. You don't really have to simplify yours if you don't want to, but it just looks a lot neater once it's simplified. So you're just going to get 1 point for the answer on this one because, again, it was pretty straightforward. All right, the next question says find the particular solution y to the differential equation with the initial condition f of -1 equals 2. So again, just like I was talking about when we did the differential equations keeper, a lot of times Taylor series and differential equations can go together. So I'm going to start with my my differential equation. I'm going to go ahead and factor out the x squared so that I can separate this a little bit nicely. So when I factor out x squared, I'm able to move this 6 minus y to the other side. From there, I'm going to integrate it, making sure I remember to u sub, right? So making sure that that ln is negative because of the negative y. From there, I'm going to plug in my initial condition and simplify. Solving for c, I get 1/3 minus ln 4. I'm going to take that c and plug it back into my original equation, multiply my equation through by a negative, my entire equation, understanding that that ln 4 part, the 4 can drop down. Then I'm going to move what I did was move my y over and then the 4e part to the other side, make sure you check your initial condition that this actually worked, because remember, with absolute value, it could have been plus or minus. So you want to make sure, plug in that initial condition to make sure like you're actually getting the right answer. In other words, plug in -1 for x, make sure that you get 2 out for y. So I get 1 point for the separation of variables, 2 points for the antiderivative, 1 point for the constant or the c, 1 point for using my initial condition, and then 1 point for solving. All right, the next question, we have a Maclaurin series for e to the x, which we do have memorized, and they're giving us a function f defined by e to the x minus 1 squared minus 1 over x minus 1 squared. They also tell us that f of 1 equals 1 and has the derivatives of all orders, so I can take derivatives all the way up. All right, so the first part says, write the first 4 non-zero terms for e to the x minus 1 squared about x equals 1. So generally, I would have to like build this like f of 1 and then f prime of 1. But because they already kind of centered it by saying e to the x minus 1, they're already centering it for us, I can literally just build it into my known Maclaurin. So I'm going to start with my known Maclaurin, and then I'm literally just going to change all of my x's to x minus 1 squared. From there, I'll just simplify it out, clean up my general term, and I get my final answer. So I'm getting 1 point for the first 4 terms and then 1 point for my general term. All right, so the next question says, take that series that you wrote out from part A and then write the general term for f, right? The first 4 terms and the general term for f. So f, they told us, was this e function minus 1 over x minus 1 squared. So I'm going to take that series that I wrote out in part A and subtract 1 from it. And then I'm going to take that and divide every term by x minus 1 squared. Cleaning that up, I get 1 plus x minus 1 squared over 2 plus x minus 1 and a fourth over 6, and so on. And I also cleaned up my my general term. All right, so for this one, I'm going to get 1 point for the first 4 terms and then 1 point for my general term. All right, now we have to use the ratio test to find the interval of convergence. So again, I'm going to take that series that I found. I'm going to add plus 1 to all my ends, and then I'm going to times that by the reciprocal of my original series. From there, I'm just going to clean it up a little bit, canceling out some of that factorial stuff. And I get that my limit of this equals 0 since I'm left with the n in the denominator, so a number over infinity is 0. And that 0 is less than 1. That tells me that it's converging everywhere. So my interval of convergence is negative infinity to infinity. I get 1 point for setting up the ratio test properly, 1 point for the limit, and then 1 point for the final answer. All right, so next it says use the Taylor series for f about x equals 0, or sorry, x equals 1 to determine whether the graph has any points of inflection. So again, I'm starting with my function for f. I know for points of inflection, I got to work it until I get to the second derivative. So I took the first derivative, and then I took that and I got the second derivative. Note that I didn't really simplify it because I really didn't care. Right, so I just need that second derivative, and what I see from the second derivative is that every term in this series is positive, right? Every term is positive because number one, they're all being added, but number two, because the powers on the terms are even powers. So even if x was like 0 or x was like -3 or something like that, you're still squaring it or raising it to the 4th or raising it to the 6th. So it's always going to be positive numbers. And because of that, I know that my second derivative is greater than 0 for all x, no matter what I put in there. So because I'm always greater than 0, I'm never going to actually equal 0. Like that tells me that I don't have any points of inflection.